Section 4 is called linear programming. It'll be helpful if you knew what linear programming was. So here you go, right off the bat. Linear programming is a method for finding a maximum or minimum value of some quantity given a set of constraints. That's all it is. That's not so bad, right? You probably have no idea what that even means. So we'll talk about that in a minute. Constraints, since given a set of constraints, we might not know what constraints are. Constraints are the limits or boundaries that a set of values can't cross. In other words, inequalities. In the last section, we were working with constraints, a system of inequalities that form that feasible region. Those were constraints. We just didn't call them constraints. And then here we are again, feasible region. We learned this in the last section. The region that satisfies all of the constraints. It's the shaded region. All of the ordered pairs in that shaded region are feasible solutions to the scenario, whatever that scenario might be. So we had that orchestra problem, orchestra seats and balcony seats. We wound up with a feasible region. Any ordered pair in that region worked. Or we had the pizza problem. We had veggie toppings and meat toppings. We wound up with a feasible region there. Any ordered pair in that region worked for that situation. So that's what this is saying. Finally, the other new word here, objective function, a function that models the quantity that we are trying to optimize. This is a fancy way of saying optimizing. A function that models the quantity we're trying to optimize. Usually the cost of production or some sort of profit situation, a price point, if you're trying to figure out what price you want to use. This objective function does not get graphed. The constraints get graphed. Objective function does not get graphed. So the reason that we do what we're doing in this section is basically companies that are out there are in the business of doing what? Any company is going to want to do what? Make money. Are they going to want to make just a little bit of money? No. They're going to want to maximize the amount of money that they can make. Okay? Now, they're not going to want to do what? And if they're trying to maximize how much money they make, they're going to try to minimize how much money they spend. Okay? How much they use to make something. Really, how much they pay employees. Things like that. Okay? That's what companies do. They try to make the most amount of money possible using the least amount of money possible. That's called optimizing. This word right here, optimizing. Okay? That's what companies do. Now, if you get out into the workforce and you are able to do what we are doing in this section very well, it is very possible, in fact this happens from time to time, and I've been a part of this occasionally a couple of times. It is possible if you know how to do the stuff in this section and you can apply it to the job that you get. You can make that some sort of presentation that you show your boss, and your boss will instantly say, this person knows what they're doing and you deserve a raise. If you want to advance in a company someday, know and remember how to do this section. Trust me. It works. Yeah. Okay. So graphing a feasible region. This is just like what we did in the last section here. Okay. We're just going to graph each one of these inequalities. And we're going to shade in the appropriate place. And when we shade, we'll have our feasible region. So you're either going to be given the set of constraints, which, by the way, the constraints are these right here. Or you will have to come up with them yourselves. And that's like those story problems that we did at the tail end of section 3. Once you come up with them or once you're given them, graph them. And then shade the resulting region. So basically we're in section 3 again right now. We have x is greater than or equal to 2. And if you remember, all year long I've been saying you have to keep straight. If that's a horizontal line or a vertical line, is this horizontal or vertical? This is vertical. And it goes through 2. So that's right here. And that is greater than or equal to. So I'm going to draw a solid line. And greater than values means numbers that are bigger than 2. Well, on the x-axis, that would be numbers to the right on the number line. So I'm going to shade to the right. But I'm not actually going to shade, I'm just going to mark that I'm going to the right. Y is greater than or equal to 3 would be a horizontal line that goes through 3. So I'll mark that. This is also a solid line. Now your graphing needs to be perfect. It's pretty hard for me to draw a nice straight line on the board, but you get the idea. The reason you need to be perfect is because now we are going to have to start picking out intersection points. There's going to be times where you can't do it on the graph, so you'll have to do it algebraically. But it's really nice if you draw nice, good graphs so that you can pick out the intersection points just from the graph. Then we have y, oh wait, I didn't shade. So I'm shading above, that says greater than. Got to shade up. Then we have y is less than or equal to 6. So that's again going to be a horizontal line that goes through 6, which is right there. So I'll very carefully draw in my horizontal line. And this time it says less than, so I'm shading below. So before I put that last one in there, I can see that I'm kind of confined now to, for these two lines right here, I'm confined to this region. But this line is causing me to only be over here. So right now, if there was nothing else to do, I would shade here. But we still have this final inequality here. I want to put that in slope-intercept form. Just subtract x from both sides and get y is less than or equal to negative x plus 10. 10 is not on my graph. Does it matter? It might matter if I had an intersection point that was going to be in my feasible region that was outside of the grid. But in this case, it doesn't matter. And the way that I can graph this is by just going to 10. I go to 7 here, and then I'm up at 8, 9, 10. Okay? Now I'm not going to guess where that is. I don't need to. My slope here is negative 1. So that's negative 1 over 1. Down 1, right 1 each time. So I'm going to go down 1 to what y value? 9. And then right 1 to here. Then I'm going to go down 1 again to what value? 8. And then right 1. And then I'm going to go down 1 again to 7. And then right 1. And now I'm on my graph. So I know I can put a dot there. And then I can continue. Down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. So now I can draw that line in there. It's also a solid line. And this one is having me shade below because it says less than or equal to. So I draw my little arrows down, and I can see that this little trapezoid right here, this region right here, is my feasible region. So that's what I'll shade. And if you look, every single intersection point for every one of these inequalities that I graphed is on my grid. So this is a legal graph to make. If this intersection point was off my grid, if it was over here or something, or this intersection point maybe was up here, that would not be good, and I'd have to redraw this graph and rescale it. If you use pen, you don't want to use pen in this section, because more than likely you will start graphing and find out that you have to rescale and start over. There's a vocab word here that isn't on here that you need to know. The vertex or vertices. Vertices are where we have corners in our feasible region. So I'm just going to circle in a different color so you can see where those vertices are. There's a vertex right here because we have an intersection in the feasible region. There's another one here, and there's another one here, and there's another one here. All four of those are called vertices. And you would write those as ordered pairs. We need to know vertices in this section. So we have an ordered pair here of 2, 3. We have another one, if I just work my way clockwise around, here, which is 2, 6. I'm working my way clockwise around. I have another one here that looks like 4, 6. And finally the last one, all the way over here, would be 7, 3. The problem didn't ask you to do that, but you are going to be doing that most of the time in this section, so you need to know how to do it. Vertices are just where we have corners in our feasible region. So now we're going to get into how to do the problems that are presented in this section. The vertex principle of linear programming is what allows us to do what we're going to do. So it's very important that you understand this. If there is a maximum or a minimum value of the objective function, then it occurs at a vertex. It says it occurs at one or more vertices of the feasible region. So if I'm looking for the maximum or the minimum, I'm looking only at vertices of the feasible region. That's why you need to label your vertices. Figure out what they are. You'll see how to work with that in a minute, but this is the key idea here that you absolutely have to know. All right, so here is how to do optimization with linear programming. The linear programming part is coming up with those constraints. They're all linear inequalities that you come up with. That's why it's called linear programming. So this is like your important safety tips section. Otherwise, you might wind up with like a severed hand or something if you don't follow these rules exactly. Rule number 1, define the variables from the information given. Just like any story problem that we've been working on. Always define your variables first. Then, write the constraints. Your system of inequalities, just like in section 3. Nothing new there. Using the given information. We can do that already. Number 3, write the function. That means the function that needs to be optimized, the objective function. So I'm going to write objective function here. And decide whether you're supposed to look for a maximum or a minimum value. The problem will tell you. It'll say what maximizes profit or what minimizes cost, okay? That tells you whether you're looking for a maximum value or a minimum value. Then graph the system. We know how to do that. Then find the coordinates of the vertices of the feasible region. And I just showed you how to do that. Then substitute the coordinates of each vertex into the function, and that's the objective function again. And then what you're going to do is, if you're trying to maximize, you're going to select the greatest result. If you're trying to minimize, you're going to select the least result. And that will be the maximum or minimum value. The coordinates that gave you that maximum or minimum value are the number of each type of whatever it is that you're doing. Shoes and shoelaces, or pizzas, meat toppings and veggie toppings, or whatever it is that you're using. That ordered pair tells you how many of each maximizes whatever or minimizes whatever the situation is. So refer back to this list of steps and follow them for each optimization problem. This probably doesn't make a whole lot of sense to you right now, just because you haven't seen any problems done. But once you see a problem done, you'll understand why all these steps are here. So this is kind of for your reference. If you're graphing by hand, you must be accurate as you graph. You have to. So be very careful. All right, so for example, what point in the feasible region for the given constraints, so the given constraints are right here, maximizes P for the objective function P equals 2x plus y. So that is your objective function right there. I've already given you the constraints. All you have to do is graph them and pick out all the vertices, okay? The vertices will go in your table, x comma y here. Your objective function is 2x plus y. And then our results will go here. So we just graph it. We have x is greater than or equal to 0. That will be the vertical line, and greater than or equal to means to the right in this case. Then we have y is greater than or equal to 0. That's the x-axis. So I'll draw that line in there. And then greater than tells me to shade above. So I'm restricted already to the first quadrant. Solve the first inequality for y to put it in slope-intercept form. I move the x over and I get 2y less than or equal to negative x plus 5. Divide both sides by 2 and I get y is less than or equal to negative 1/2 x plus 5 halves. So that plus 5 halves is kind of a bummer. It's not that big a deal. 5 halves is 2.5. So I'll just go up to 2.5, which I'm going to say is right there. And then I have a slope of negative 1/2. So I'd go down 1, right 2. Well, down 1 is right there, right 2, over to here. Down 1 is there, right 2, over to there. Down 1, right 2. Reverse it, up 1, left 2, up 1, left 2, up 1, left 2. That's also a solid line. Most of the things in this section are going to be solid lines. So I draw in my line, and I'm going to be shading below. So now I can see that I'm kind of confined to that little triangle right here in the middle, but I still have one more line to draw in. So I put the second one in slope-intercept form. That gives me negative y less than or equal to negative x plus 2. Got to multiply everything by negative 1, which reverses my inequality symbol. Y is greater than or equal to positive x minus 2. So I have minus 2 on my graph, a slope of 1. Reverse it. Solid line, greater than says shade above. So there we go. Shading above my feasible region gives me this weird looking, kind of almost kite-like shape right there. So the next thing to do is to pick out your vertices. Everywhere that we have a corner, we have 0, 0 is a corner. We have, I'm going clockwise around, 1, 2, 0, comma, 2.5. So 0, 5 halves. Over to this one now would be positive 3, positive 1. And then finally 2, comma, 0 right there. So we'll figure out how to do the rest of this next time.